Hello everyone, hopefully you're doing well. In this video, we're going to complete section 5.3 in chapter 5, discrete probability distribution. In this section, we're going to take a look on another distribution that we call Poisson distribution. That we're going to describe a probability distribution, Poisson distribution, and five probability values for a Poisson distributions. So there is one distribution we haven't covered exactly. That was a geometric distribution. Probably in a different video, we're going to see some geometric distribution in itself. This is the formula for it. So if you're looking for probability of X for the geometric distribution, the formula is P times Q X minus 1. So for this one, the difference between geometric distributions and binomial distribution we already covered in the previous chapter. For the binomial distribution, you have a number of trials, and you see for the geometric distribution, you don't have a number of trials, but you have exact success. What happened? Let's say, for example, um, in a basketball game, if there is a foul, there are three free throws if the foul is out of the semicircle area. So three free throws, that's a number of trials, and for each trials you have the same probability of success, and they are all independent from one another, and you have probability to have zero success, one success, two success, and three success, out of three. That's we call probability of success. But that's we call binomial distribution. But for geometric distributions, it's like you need to try until you succeed. For example, I need to make a call to, to sell a new iPhone. I am a salesperson, a marketing, I work in the marketing, but you know what? I want to make calls to sell. So my first success would depend on when I sell something. So I may do it in the first call, in the second call, in the third call. Maybe I will do it on the 11th call. My first success would come on my 11th call. I don't have a number of trials. I can try until I succeed. So we call that geometric distribution. But now, another distribution is the Poisson distributions, as we said. Remember in section 5.1, we introduced general discrete probability distributions, where we said, oh, you have a discrete probability distribution, you have a distribution, a probability distribution. If you have a probability between 0 and 1, the total of all probabilities is equal to 1, and you have numerical data, not categorical data. In section 5.2, we considered binomial probability distributions, all right, which is one particular category of discrete probability distribution again. So here what we do, we introduce Poisson distributions, which is another category of discrete probability distribution. So in terms of definitions, as you see, for the definitions, we said that, there are different ways of, define Poisson distributions. Said that Poisson distributions are used with occurrence of an event over a specified interval. And here are some examples. So let's say you want to know, you still deal with probability of success and failure in a different way. Remember, binomial distributions, we said, oh, you have a number of trials independent from one another, and you have the same probability of success for each trial. For geometric distributions, we said you need to try until you succeed, like making phone calls. Poisson distributions, you would find your probability based on an average. This is the only distribution with the average so far out of these three. You can have those some examples, like if you want to know the number of automobiles accident in a day, you would do it based on the average, thing that's already exists, the mean. Number of patients arrive at an emergency room in 1 hour, number of internet users logging onto a website in one day. There are many, many different examples. Number of Atlantic hurricanes in 1 year, number of spelling errors on a page, spelling error on a page, numbers of machine failures in a month. So you use those means or the average to find the distribution. So we said a Poisson probability distribution is a discrete probability distribution that applies to occurrence of some event over a specified interval. The random variable x is the number of occurrence of the event in an interval. The interval can be time, distance, area, volume, or some similar unit. So we can do that. We have a formula for it. So the formula to find the probability of success using probability Poisson distributions, we have that as P of X equal mu power X times E negative minus mu over X factorial. So remember here, mu is the population mean. We're going to see it on the next slide anyway. Okay. Remember, X, number of success. And once you have these two, everything is okay, because remember, E is a natural exponential. So it's the values is 2.718. It's a irrational number, so it's indefinite. There are a lot of digits, but know that in your calculator, check for the e power x. So that's, you don't need to e is in your calculator, e power x. You can just hit it. And of course, if you want to do some Poisson distributions using calculator, you can, because in terms of formula, you still, if you use ti 83 or 84, let's do 84. You do, first of all, distribution, TIS, look for its second functions and a key. Then after that, you can either hit Poisson PDF for exact values. I mean, in the Poisson PDF, you have the mean, and X, no N, sorry, I put N. So you need to have the mean and X. Or you can do CDF, so Poisson CDF, when you deal with less than the inequality, less than or equal to, greater than or equal to. So it's gonna be the mean and X. It all depends. Remember, this one, CDF is for inequality, PDF is for exact value, equality. Now, we have some other techniques we can use to identify when we deal with a Poisson distribution. Requirements for the Poisson probability distribution. The random variable x is the number of occurrence of an event in some interval. The occurrence must be random. The occurrence must be independent of each other. The occurrence must be uniformly distributed over the intervals given, right? And Poisson distribution parameters and properties. Parameters of Poisson distribution: the mean, you have the mean, and of course, the standard deviation is the square root of the mean. We can use it that way. In terms of properties of this, a particular Poisson distribution is determined only by the mean. It's about the mean. This is the only distribution with the mean. Binomial distribution doesn't have the mean, and geometric distribution doesn't have it. A Poisson distribution has possible values of x. Remember, you do P of x equal mu power x times e power negative mu over x factorials. Remember, x factorials, if we do 5 factorials, it's like we have 5 times 4 times 3 times 2 times 1, right? So I believe that would give you 120. So if you do factorials, it's multiplication in ascending order. Other things you need to remember about this, we can also use Poisson distribution to approximate the binomial distributions. We need to verify that at least n is Poisson distribution, sometimes used to approximate binomial distribution, and we have a large n, and p is small, like 5%. One rule of thumb is to use such an approximation when they follow. You see n is greater than whether or equal to 100, but NP is less than or equal to. That means P is so small, P small, N large. Okay? So greater or equal to 100. So you can use that. Because in this case, there are two requirements we do. If both requirements are satisfied and we want to use the Poisson distribution as an approximation to the binomial distribution, we need a value for the mean, mu. That value can be calculated by using the formula. Like for us, we have the mean equal NP. Or we can see it here. That's exactly what we do. Mean for the Poisson is this way. All right. Now, let's do a few examples very quick and make sure we get everything correct. Let's go with the first one. We said assume that Poisson distribution apply. Usually we tell you what distributions you need to use. If that's not the case, then you can always check again. We said assume the Poisson distribution that the mean number of hurricanes in the America is 5.5. Oh my God, we have the mean. That's the most important part we need when we perform Poisson distributions. All right. So because remember Poisson distribution, this is the formula: mu power x times e power negative mu over x factor. So once you know the mean, you can answer any questions. One thing I'm going to do here to make sure that we answer everything correct, I'm going to put this one smaller. Now you see what it is. Let's put it smaller. I'm going to put it 14 so I have enough space. Yeah, let's do it. We can do A, it all depends on how we want to do it. But you know what? How about we start with the first one, find the probability that in a year, there will be 7 hurricanes. That means X here is 7. If you do probability that X equals 7, would be the mean, which is 5.5. All right, we're gonna have 5.5 power 7 times E. We don't need to do 2.718, but because in the calculator we can find power 5.5 over X, which is 7 factorial. So if you do this one, answer must be something like 0.123. I'm going to go with B down here so I have enough space. Maybe the space would be enough. In a 118-year period, how many years are expected to have 7 hurricanes? So in a 100, remember the probability that you have 7 hurricane is 0.1, 12.3%. In 118 years, in 118 years, the expected values with 7 hurricane, expected value would be 118 times for 7 hurricanes. Let me erase because I want to make sure you see what I do. Expected value for 7 hurricanes in 118 years. It should be 118 times the probability that to have 7 hurricanes in a year. So that would be, you multiply these two. Expected value in this case would be 4.5. So the expected value, remember for C, how does the result from B compare to the recent period of 118 years in which 14 years have seven hurricanes, you know? So in this case, remember the expected values of 14.5 years, I mean, expected value, seven hurricanes, is very close to the actual value 14 because they said you can do 14, we have 14.5. So they are, so in this case, the Poisson distributions works well. So yes, we'll see, they give us 14 years, but we find 14.5. So Poisson works. Yes, Poisson distributions. All right, we're gonna say works well, right? Find a probability that in a year there would be no hurricane. Well, that means here they said D, there would be no hurricane. That means X is equal to 0. If X equal to 0 for D, all right, X equal to 0 for D, I do A, B, C, now we are in D. Probability that X is equal to 0, that means using the formula, the mean is 5.5 power 0 times E power 5.5 over 0 factorial. So remember, for us, we said 0 factorial is 1. So because remember, you cannot divide by 0, but 0 factorial is 1. We expect the answer in this case to be 0.0049. No, 0.00409. That would be the answer for D. Let's see if I can do two more, or maybe I would leave you with the rest. And I think it asks you the same type of questions. How does the result from part A compare to the recent period of 118 years in which there are 2 years without any hurricanes, any hurricane, there's the Poisson distribution work well. Again, here, look at that. In 118 is there, the expected values, the expected values now to have 0 hurricane. Look, if we do expected values for, no, that's E. Expected values of how many? How many years I expected, how many 18 years? I expected to have no hurricane, of 0 hurricanes in 118 years. Again, we do 118 times 0.00409. What this one gave us is 0.5 year, right? So 0.5. So for us, if you look at F as a questions, how does the result from E compared to the recent period, years in which there were 2 years without any hurricanes? So here also the expected values is 0.2 years. That's very close to 2 because remember, 2, I mean, very 2. I think, yes, you can still have, for F, can I write it there? Yeah, Poisson works. 0.5 to 2, Poisson works well. I mean, do not say Poisson. We need to keep it Poisson because that's the name of a mathematician. All right. So let's say for G, if we have enough space to put G, again, those are the same type of questions, but I believe if I leave this one for you, you can do GH I, because those are the same type of questions. I'm going to leave it for you to enjoy. Now, let's go with the second examples here. We said for these examples, all right, we're gonna check where it says in a recent year in New York, all right, in a recent year, 365 days. We want to make sure that New York University Langone Medical Center had 5,942 births. Find the mean number of births per day. Per day. If you have in total, look, if you have in total, if n is 5, no, it's number of birth. So in per day, if you have the whole thing, that's 5,942 over 365, right? So that's how you're gonna find the answer then for the number of births. So that would give you 16.3 births a day. Well, actually, you're gonna have 16.3. You either have 16 or you have 17. So you can round up and some points round up, round down, because at the end, the answer would be different. Now, the next question is find the probability that in a single day, all right, remember this mean right there, that's another mean, right? The number per day. So we're going to call it, this one is the mean, okay? Right, per day. Now, that's the average. Now, for 2, find the probability that in a single day, there are 16 births. So we said there are 16 births. That means for us, X equals 16. Remember, they said here, we just put it down, but use the Poisson distributions. Again, remember, Poisson distribution for us is mu power X times E power negative mu over X factorial. So we know the mean is 16.3 power 16 times E 16.3 over 16 factorial. So in this case, answer for us would be 0.0989. Number 3, we can answer very quick, or decide to go slower. Find the probability that in a single day there are no births. No births, that means X is equal to 0. Would 0 births in a single day be significantly low or significantly high? So the first thing to do, remember, is to find that probability. So for us, probability that X equal to 0 would be the mean power X times E 16.3 over 0 factorial. So to do this again, the answer, maybe we're going to have something that is really, 0. Check your calculator. Maybe when I do it, I find how many zeros. I would put 7 zeros, 3, 8, 4. 1, 2, 3, 4, 5, 6, 7, 3, 8, 4. All right. So they said, would 0 births in a single day be significantly low numbers? Well, it's you need to verify, because we need to find the mean. The mean would be low. Yeah, the mean is below the mean. We need to find the standard deviation. Remember, it's n. We take the square root. So definitely, it's a yes. Yes. 0 births will be significantly low. Yes, will be significantly low for SL, significantly low. because, 0 is really under what the mean minus 2 standard deviation that we don't really do here. Another example that, because remember we said this chapter, we're gonna go very quick in doing it because I have time to do more and more and more later. But for now, we said that neuroblastoma, a rare form of cancer, occurs in 11 children in 1 million. So remember the 11 children in 1 million. I believe they already give you something. So its probability is 0.00011. 4 cases that indicate X as 4 occur in Oak Park, Illinois, which had 12,429 children. Assume that the neuroblastoma occurs as usual. Find the mean. Remember, in this one, to find the mean, let's find the mean. Okay. Remember, in this case, to find the mean, we only say is NP. What is N again? For us here, N is 12,429. What is P? The probability. The probability is very, very small. It's a 0, 4 other zeros, 11. So to find the mean, we take 12,429 times 0.00011. So which is the mean is what? Let's go, it's 0.1367. So let's go with that for the mean, because now they ask us for the mean. And using the unwanted means from part A, unrounded mean from part A, find the probability that the number of neuro cases in a group child children is 0 or 1. When we said it's 0 or 1, 2, we do probability that it's 0 or it's 1. So that means probability that X equals 0 plus probability that X equal 1. Remember the formula to using Poisson would be probability of X would be mu power X times E power mu over X factor. So we're gonna do it twice. We remember the mean in this case would be 0.1367 power 0 times E power 0.13, because this is the mean. No, sorry, I messed up with the mean. Yeah, no, I don't mess up with my mean. Okay, that's the mean, definitely. 1.367 over 0 factorials plus 0.1367 power 1x times E 0.1367 over, okay, over 1 factorials. So answer in this case for number 2, when you do all of this, it gives you 0.991463. So that will be the answer to have 1 or 2. What is the probability of more than 1 case? More than 1 case, usually, if you know more than 1 case, 3, probability that X is greater than 1, strictly greater than 1, we're gonna do it. It would be 1 minus 1 minus probability that X is less or equal to 1. Something we already did, because less equal to 1, that means probability that X equals 0 plus probability that X equal 1. We already have these two, so we can do 1 minus 0.991463. I don't need to redo 0 and 1 and subtract it from 1. I can do it right here because we had it before. So it's going to give us 0.00854. Now, the last question is D, number 4. If we say, does the cluster of 4 cases appear to be attributable to random chance or why not? We would say here, if you look closer, it's not, because the probability of more than one case is extremely small. Look at that. More than one case is like 0.00854. In this case, the probability of getting as many as 4 cases is even smaller. So hopefully, this one help you to understand this chapter better. As I said in a different video, we're going to show you how you can compute Poisson distribution, binomial distribution. I mean, like, binomial distributions, or, just do some discrete probability distribution using calculator or Excel. Let me know if you have any questions. I'll see you in a different video. Take care.